So, hello again students, and welcome to the homework session. Following the theory session of this nugget, you shall have an idea of how to make the simplest and roughest estimate of the energy needs for transport of material. And one of the most important things for you to learn is not to be afraid of simple estimates. You may argue, and that is correct, that the simple estimates have no real value and cannot be used for serious judgments. But that is not the point. The point is to give you an idea and an insight of the orders of magnitude of energy input required for some of the steps in the supply systems. Of course, I could just give you numbers, but doing that would be no help for you once you have to do an analysis by yourselves. So what I want to do is to give you the self-confidence to do simple estimates based on reasonable assumptions, and then use these estimates, applying a critical mind, to lay out the overall strategic plans. For detailed planning, you will then have to do a more detailed analysis, of course. Remember now that economy as such has nothing to do with money. So what you shall know after this nugget is how to estimate the cost of operations as they appear in the energy budget. Typically, for the machines mentioned, is the total expense between 3 and 10 times higher than the expense for the diesel fuel. So in case you want to estimate the expense, the amount of money that is, just take that factor. But the cost remains as an energy input in the energy budget. Let us now do another cost estimate. A small chipper, like the one in this slide, will be very uneconomic. But I have selected this to make the estimate since it will give us a worst case scenario. The data for this chipper can be found on the web page indicated at the bottom of the slide, at least right now, by the end of 2019. But since this is a commercial page, I cannot guarantee that the data will still be available when you take this course. So here are the crucial data. Basically, you need only two values to make the estimate: the engine power and the capacity. To be sure to overestimate the energy input, we assume that the engine is running at full power. And then we assume that the real throughput is only a fraction of what the manufacturer claims. In this case, I have assumed a production rate at only 20% of the maximum. So again, we find that the cost of the operation is in the order of 1% of the energy contained in the biomass. That was about what we found for the transport. And then, in the previous nugget, we found a total cost about 5% for the harvesting and collection. But what we have done now are only energy estimates. Each and every time you load or unload the material to or from any type of vehicle, there will be a loss of material. If you know nothing else, then assume that you lose 1% of the amount handled in every operation. So if 1 ton of material arrives at a terminal and is unloaded, then 10 kilos are lost. And then the 990 kilos are again loaded for the final transport, and 9.9, or make that 10, kilos are again lost. In the theory session of this nugget, I said that most energy carriers will exhibit losses of between 5 and 15% until they reach the end user. And the same holds true for biomass. So let us now have a look at how to use these data through a supply system. Starting with 1 ton of semi-dry lignocellulose and following that through a realistic supply chain, we find the following. In the harvesting and collection operations, we assume the energy cost at 5% of the total energy in the material. To that comes losses of material, bark, dust and such, while handling the material. In this case, Since we assume that the quality of the material does not change, may both these losses be added together, and in the slide I have written out the total loss expressed only as a mass loss. In the next nugget I will modify this a bit, because storage will have an effect on the quality of the material. But for the moment, as the quality and the heating value do not change, we can treat mass and energy as directly proportional. So taking the mass and the energy losses into account, we then find that the material in the windrow represents 94% of the original energy, and I express that as an equal amount of 940 kilos. Next comes chipping and loading. Following the previous estimate, I assume a chipper energy input equal to 1% of the energy in the material, and then I assume handling losses at 1%. So the material loaded onto the truck will then represent 92.1% of the original energy. And I express that in this example by saying 921 kilos. Following the transport is the material unloaded at a terminal, and again we have an energy input for the transport equal to 1% of the total energy, and then we have material and handling losses as the chips are unloaded at the terminal. Finally, the chips are loaded on board a truck, 1% handling losses, hauled to the end user and unloaded, again with the loss of material. You will notice that the terminal in this example is closer to the end user than to the felling site. The transport from the felling site to terminal required 1% of the energy, but the transport from the terminal to the end users requires only half. Expressing all the costs and losses in terms of energy, in this example further simplified as the quality was assumed constant throughout, makes the total efficiency estimate for the system very simple. In this case, as you see, is the total supply system efficiency 88%. So what you shall do now is exactly what I did on the previous slide. Select a sample supply chain in your own region or in your own country if that's easier. It is critical that the chain you pick does not include any quality changes of the biomass. So no forced drying, no pelletizing, no gasification, but baling or cutting into pieces or such is okay. Put it this way, the heating value of the material may not change during the chain you select. Then describe the supply chain in terms of unit operations. Chapter 3.0 in the Busy Plan Handbook tells you about unit operations. And I have talked about some unit operations in the previous nugget and in this nugget. And then try to find values for energy input and material losses in the system you have selected. If you cannot find real data, then do estimates the way we have done, but do it for the machines actually used in the chain you're looking at. And then evaluate the total system efficiency, just the way I've just shown you.